Okay, YouTube, in this video I just want to look at a couple of special instances when we solve linear inequalities. Sometimes we get special solution sets, as well as looking at how we deal with what we call a compound inequality. So let's look at first this checkpoint 6 here. We want to solve each of these inequalities and then graph our answers. When we look at this though, we need to simplify the left side. So it simplifies out to 3x plus 3 is greater than 3x plus 2. And really what I want you to understand here is, when will 3x plus 3 be greater than 3x plus 2? And for many instances, this is always going to be true. As a matter of fact, so many that we cannot list them all. So any number you plug in here, this is always going to be true. The way we can determine this, though, is we could just try to isolate the x by getting it off of one side. And what you find out is you end up with a statement like this: 3 is greater than 2. And so basically, we would say that the set of solutions here, if we're going to graph this, is the entire set of real numbers. So here's your solution set right there. And we would say that we would list this in interval notation as negative infinity to infinity. And basically what this means is all real x values is going to cause this statement to be true in the first place. So you can look at this as like when we solve equations, an identity. Okay, this is always true. Now, letter B here, you might kind of foreshadow what's going to happen. If this is an identity, then what's this going to be? Well, we say x plus 1 is less than or equal to x minus 1. I mean, think of any number you plug in here and add 1 to it. Is that ever going to be less than or equal to any number, that same number, and you take 1 off of it? It's just never going to be true. But trying to solve this again, when you go through the processes that you're used to here, we'll go ahead and subtract this. I end up with a statement 1 is less than or equal to negative 1. You need to consider this because it's not true, ever. It's never true. So we say no real solutions, no solutions. Basically, I'm going to say no solutions. And if we were to write this in interval notation, we couldn't. As a matter of fact, you draw your whole number line and we'd say, none of these numbers are going to do this. So we'd say the solution set really is the empty set, or we can call this the null set. So we say no solutions. So this last problem here, I just want to look at this. Sometimes you end up with what we call a compound inequality. Excuse me. So compound just means like more than one thing going on at a time. And I get a lot of people, they're like, hey, I really don't know how to deal with this. And what we're going to do is we're just going to treat this as like a long chain of reasoning. So just like 1 is less than 2 is less than 3, if I were to say add 1 to this and add 1 to this and add 1 to all 3 of these instances, I'd have 2 is less than 3 is less than 4. The point here is this: we'll treat this like an equation that has 3 different parts to it, or an inequality that has 3 different parts to it instead of just a left side and a right side. And what we do to one of those parts, in order to maintain this relationship, we have to do to all of the rest of them. So in reality, this could be 1 is less than or equal to 2x plus 3 is less than or equal to 11 is less than or equal to something is less than or equal to something. And we'll just operate on everybody. So for instance here, I'm going to need to subtract 3 from the middle to isolate the x. But that means I need to subtract 3 from the right, 3 from the left, and any other relationship in here. So what we end up with is just 2x in the middle. Looks like we have is greater than or equal to, and this is less than. And then 1 minus 3, well, that's just a negative 2. And 11 minus 3, that's just an 8. So this statement is equivalent to the original statement. The only thing we have left to do is now divide everybody by 2. And so since we're dividing by a positive, I do not need to switch these inequality signs here. And x is now by itself. 8 divided by 2 is 4. And then negative 2 divided by a positive 2 is a negative 1. So this right here is the set of solutions. Now graphing this, we do want to make sure we graph this. We'd say, well, x is between and including negative 1, but not including 4 there. So we'd say if this is 0, here's negative 1. 1, 2, 3, 4, 5. Here's 5. We would illustrate this by saying including negative 1, but not including 4. All numbers in between this right here is the set of x values that we're looking at there. X belongs to this set. So in interval notation, we would say from negative 1 up to, but not including 4. Cheers.